Hey, welcome back. In this week's videos, we're going to discuss some graph parameters that are used in the design of VLSI circuits. VLSI stands for Very Large Scale Integration. And it's a process for creating integrated circuits by combining millions of transistors onto a single chip. VLSI started becoming used in the 1970s when MOS transistors, and we mentioned MOS in an earlier video, it stands for metal oxide semiconductor. So when these MOS transistors started becoming widely adopted, that's when very large scale integration started getting commonly used. And before VLSI, most integrated circuits had pretty limited functionality. But with VLSI, integrated circuits were able to do many different functions, ones that would have been done on separate integrated circuits before, but VLSI circuits allowed you to do all these different functions all in one chip. So in both of the videos for this week, we're going to focus on some graph parameters which can be applied to VLSI circuit design. And there are also some other applications besides circuit design. The first graph parameter that we're going to look at, which we will focus on in this video, is the crossing number of a graph. And before we define the crossing number explicitly, we're going to motivate the definition in terms of VLSI circuit design. So suppose we have some VLSI chip and we represent it as a graph, and the nodes / vertices of the graph will correspond to macro cells in the chip. And edges in the graph will correspond to wires that connect the nodes / vertices, which are the macro cells. So the chip designer needs to place the macro cells on a circuit board, and they also need to place the wires, and their goal is to avoid crossings between the wires since they lead to undesired signals. So one way to avoid crossings is whenever you have two wires that cross, you change the layers of one of the wires. So doing this, changing the layer of one of the wires whenever you have two wires that cross, each time you change the layer is called a contact cut. And if you do many contact cuts, this forces your chip to use more area, and this makes the chip also more likely to be faulty. So you don't want to use many contact cuts. It's good to use as few contact cuts as possible. So if your strategy in designing the circuit is to use contact cuts whenever there's a crossing between two wires. And the goal is to use as few contact cuts as possible. The goal in terms of the graph is to minimize the number of edge crossings. And this is what motivates the definition of the crossing number of the graph. So we denote the crossing number of a graph G as CR of G. And CR of G is defined as the minimum number of edge crossings in any plane drawing of the graph G. And a plane drawing is just a drawing of the graph in the plane, where vertices are drawn as points and edges are drawn as curves that connect the points. So one thing that you can observe right away is that every planar graph can be drawn in the plane with no edge crossings. And any graph that can be drawn in the plane with no edge crossings is a planar graph. So we can say that G is planar if and only if the crossing number of G is equal to 0. And we can also observe a trivial upper bound on the crossing number. So if we have a graph G and G has a total of E edges, I claim then that the crossing number of G is at most E choose 2. And this is because if we have a graph G, we can draw G just with the vertices as points. And we can draw the edges as straight lines between the vertices, straight line segments. And if we draw the edges like this, any pair of edges will intersect at most once, because two line segments in the plane only have at most one point of intersection. They might have 0, but at most they have 1. And if we have a total of E edges, there's at most E choose 2 pairs of edges. So if there's only one intersection point at most for every pair of edges, and there's E choose 2 possible pairs of edges, then we can say the crossing number is going to be at most E choose 2, because it's possible to draw our graph G with at most E choose 2 crossings. And it might be possible to draw it with far fewer crossings than that. But this upper bound holds for any graph with E edges. Also note that E, if G has order n, then we can say E is less than or equal to n choose 2, which equals big O of n squared. So the crossing number of G, since it's less than or equal to E choose 2, which equals big O of E squared, we can say that the crossing number of G equals big O of n to the 4th, where again, n is the order of our graph. And we will see that this bound, big O of n to the 4th, is actually sharp up to a constant factor. So we'll see multiple graphs for which this is sharp up to a constant factor, and we'll actually prove that it's sharp up to a constant factor for multiple graphs later in this video. Before we prove any results, we're also going to consider another motivation for the crossing number. And this is an earlier motivation. So the motivation of VLSI circuit design, that motivation was from the 70s because VLSI started becoming commonly used in the 70s. And the papers that applied crossing number to VLSI circuit design were from later than that, so the 80s. But this application was from the 40s, the 1940s, and it's known as the brick factory problem. And during World War II, Tron was forced to work in a brick factory. He had to push wagons of bricks from kilns to storage sites. Between each kiln and each storage site, there were tracks. And at places where tracks crossed, it was harder to push the wagons of bricks. So Tehran asked how the factory, including the kilns and the storage sites and the tracks, could be redesigned to minimize the number of crossings. And as you can see, this is equivalent to asking the crossing number of a complete bipartite graph. So if you assume that there are M kilns and N storage sites, this problem that Tehran was considering was the same as the problem of calculating the crossing number of K sub M comma N, the complete bipartite graph with parts of size M and N. And so this is still an open problem. So the exact value of this crossing number is not known in general for all M and N. So for small fixed values of M or N, it is known, but it's not known for large M and N, the exact value. There are only pretty sharp bounds on it. And it's conjectured that the best known upper bound is the correct answer. So we're going to discuss how to get that upper bound. First, we can observe when M equals 1 or M equals 2 that the complete bipartite graph K sub M comma N is planar. So we observed that in an earlier class, that K sub 2N is planar, and obviously K sub 1N, that's the star, and any tree is planar. So since they're both planar, they both have crossing number of 0. And in 1952, Tehran gave some talks about this crossing number problem. And he posed this problem of finding the crossing number for the complete bipartite graph. And at least 2 people considered that problem, and they both found the same upper bound on the crossing number of k sub m comma n. So one of them was Zerankowicz, the other one was Urbanic. This is the same Zerankowicz as the one that we learned about before, the Zerankowicz problem related to the Kováry-Sillestrom theorem. So the 0-1 matrix problem that we saw. In other words, the problem about bipartite graphs, avoiding other bipartite graphs. So you can think about it in terms of bipartite graphs or in terms of 0-1 matrices. So that was a different problem, but it was the same person, same Zerankowicz. But Zerankowicz also had this result about the crossing number. And he proved this upper bound, that the crossing number of the complete bipartite graph with parts of size m and n is bounded from above by the floor function of m over 2 times the floor function of m minus 1 over 2 times the floor of n over 2 times the floor of n minus 1 over 2. And there's a pretty simple way to see this bound. So to prove this upper bound, all you have to do is just construct some drawing of k sub m comma n that has at most that many crossings, at most the number of crossings equal to the quantity on the right side of the inequality. So I'm going to describe a drawing like this, and we'll talk a little bit about why it has that number of crossings, but I'll leave some of the work to you as well. So here's a description of it in words, and I'll do a picture next to the words. So we place m vertices on the x-axis. We don't place any of them at the origin. And we put near equal number of points on both sides of the y-axis. So I'm going to draw this up at the top. So we have the x-axis, we have the y-axis, and I have m vertices I need to place on the x-axis. So I place some number of them over here and some number of them over here. So approximately m over 2 over here and approximately m over 2 over here. I can be even more explicit about that, and I can say floor of m over 2 over here and ceiling of m over 2 over there. Though the way I drew it, it would be like that. So that's the x-axis. We have those points. And then the y-axis, similarly, except instead of m, we have n. So on the y-axis, we don't put any points at the origin, but we put near equal amounts on both sides of the y-axis. So there we'll have ceiling n over 2, and then down here we will have floor n over 2. And then once we place those points, in order to draw the case of m comma n, well, if we think about it, the complete bipartite graph with parts of size m and n, we connect all the vertices in the m part to all the vertices in the n part. So it makes sense in this drawing, we want to connect all the vertices on the x-axis to all the vertices on the y-axis. So the way I've drawn it connect all of these, and so on. So I'll just do one quadrant of this. So you can see there's a lot of crossings in there. And we want to count the total number of crossings in this picture. So we can think about each crossing, and we can note something useful about the edges in this picture. So the edges, we know that each edge goes from some vertex on the x-axis to some vertex on the y-axis. And therefore, each edge lies fully in one of the quadrants. And that tells us that all of the intersections also have to lie in some quadrant. So each intersection in some quadrant will be between two edges that are both fully contained in that quadrant. So to count the number of intersections, the number of crossings here, we can just focus on each quadrant separately and then add them up. So we can look up at this quadrant and we can think about each intersection. How do you make an intersection? How do you get a crossing? And to get a crossing, you need to pick 2 points on this axis. There's 2 points somewhere on here. You also need to pick 2 points somewhere on this one, say there and there, for example. And to get a crossing with those 4 points, you have to take this and this. So that's the way they can cross, is those two edges. And that's the only way you can have two edges that cross on those 4 points. And any crossing in that quadrant is going to be obtained by choosing some 4 points, with 2 of them on the y-axis, the positive y-axis, 2 of them on the positive x-axis, and taking the edge that goes from the bottom one on the y-axis to the most positive one on the x-axis, and the top one on the y-axis to the least positive one on the x-axis. So that gives us this crossing in the center. So if we want to count the number of crossings between edges, we can just count the number of ways to choose these 2 points from the y-axis and the 2 points from the x-axis right here. So if we have, let's say, k equals the ceiling of n over 2, and j right here equals the ceiling of m over 2, then the number of ways that we can choose 2 points on that y-axis, we just have k choose 2 ways. And then the number of ways that we can choose 2 points on the x-axis, the positive x-axis right here, we have j choose 2 ways. So that's the number of ways that we can choose 2 points on the positive y-axis, 2 points on the positive x-axis, and that gives us the number of crossings in the positive quadrant, the quadrant where both x and y are positive. And that's our number of crossings for that quadrant. And you just need to count the number of crossings for the other quadrants. And I claim that when you add it up, it gives you this quantity in this bound right here. So this upper bound that Zerankowicz and Urbanik found. And note that this k right here, k is the ceiling of n over 2, and j is the ceiling of m over 2. So in order to prove that upper bound, it might help to consider when n is even or n is odd, and when m is even or m is odd separately. That might help. It's possible to keep it all in one case, but you can also break it up. And I leave that as a problem for you to think about. So prove or disprove that the construction that I have described there gives the claimed upper bound of Zerankowicz and Urbanic. And something that's kind of interesting here is when Zerankowicz proved this upper bound originally, he claimed that he also was able to prove that the upper bound was optimal. So he claimed that this upper bound is the actual crossing number. And he proved it supposedly. And I think it took over 10 years for someone to find an error in the proof. And it's now known as Zerankowicz conjecture that is the actual value of the crossing number of the complete bipartite graph. But this is still an open problem. Another family of graphs that we've seen a lot in this class, for which the crossing number is open. So besides this one, so crossing number of the complete bipartite graph is open. And so is the crossing number of the complete graph. So these are both open problems. But it's also known that both are on the order. So the complete graph, this one is known to be on the order of n to the fourth. And the crossing number of the complete bipartite graph, that one also has bounds that are sharp up to a constant factor. And we're going to talk about why we can obtain sharp bounds up to a constant factor. So this one in particular, we're going to prove a more general lower bound. So we already have seen why we can get the big O of n to the fourth upper bound. The big O of n to the fourth upper bound, that holds for any graph of order n. So that's immediate because complete graph of order n has n vertices. But we're going to see a lower bound, a general lower bound on the order of omega of the number of edges cubed divided by the number of vertices squared. So for the complete graph, that gives us a lower bound on the order of n to the sixth over n squared, which is on the order of n to the fourth. So that's how we get a theta of n to the fourth for the complete graph. So we're going to see how to prove that. And it's known as the edge crossing inequality. And here is one version of the inequality. So if you have a graph G of order n with the number of edges E greater than 4 times the order, 4 times n, then the crossing number of this graph is at least E cubed divided by 64n squared. And it's possible to get a sharper lower bound than this.
So you can improve the constant. You can prove CR of G greater than or equal to E cubed over, I think it's 29 n squared. But you need to assume that the E is larger relative to the order. So E greater than 7n. So as you can see, both of these bounds are omega of E cubed over n squared. And for the purposes of this video, I don't care about the constant at all. Even if it was E cubed over 1,000,000 n squared, it wouldn't matter. So we're just trying to prove this omega of E cubed over n squared. That's our goal in this video. And we're going to use a tool from a toolkit of tools that we've used a lot. And that toolkit is the probabilistic methods. So we're going to use that again. And before we use these probabilistic methods, first we're just going to observe a bound that relates the number of edges, the crossing number, and the number of vertices. So the bound that we're claiming, that's also a bound that has those properties. So it does relate the crossing number, the number of edges, the number of vertices. But the bound that we're going to prove first, it's going to be kind of a simpler bound, but it's going to be helpful to combine this simpler bound with the probabilistic methods, and that'll give us the bound we want. So first, let's look at this simpler bound. And the simpler bound that I claim is that the crossing number of G is at least the number of edges in G minus 3 times the number of vertices in G. And I'm going to annotate that just to make sure it's clear there. So E is the number of edges in G, and N right here is the order of G. So when otherwise not defined, N is always the order of the graph. So let's talk about why this bound is true, because I haven't proved it yet. So we need to figure out why that makes sense. One thing we did prove in an earlier video is that if you have a planar graph with n vertices, in other words, a planar graph of order n, it has at most 3n minus 6 edges. So we proved that by showing that every maximal planar graph has exactly 3n minus 6 edges, and every planar graph can be turned maximal by adding edges to it. So every planar graph of order n has at most 3n minus 6 edges, since the maximal planar graphs of order n have exactly 3n minus 6 edges. And 3n minus 6, this is strictly less than 3n. So every planar graph of order n has fewer than 3n edges. And we're going to use that. So we'll take our graph G, which might not be planar, and we'll consider some drawing of G in the plane, a plane drawing of G. And specifically, this plane drawing of G will have exactly CR of G crossings. So the crossing number of G, remember, is the minimum possible number of crossings in a plane drawing of G. So there exists some plane drawing of G that has exactly CR of G crossings. So we're going to consider such a drawing, and we're going to draw it, and we have this drawing of G that has the crossing number of G crossings. For each crossing in this drawing of G in the plane, we'll remove at most one edge. It's possible that we'd be able to get rid of multiple crossings using the same edge, but in the worst case scenario, we only need to remove a single edge for each crossing. So we remove up to CR of G edges to get rid of all of the crossings. And once we get rid of all of the crossings, once we remove at most one edge for each crossing, the resulting graph will be planar. And so I leave you with a problem. So given what we've just discussed about here, this operation we did where we started with this plane drawing of G with CR of G crossings, and then we removed at most an edge for each crossing in order to turn this graph into a planar graph. So why can we then conclude the inequality in the top bullet? So why does this operation that we just did give us that top inequality? So I'll leave that to you to finish off getting that last inequality from the last slide. So we have, for any graph G, the crossing number of G is greater than or equal to the number of edges in G minus 3 times the order of G. And we want to prove this. So I'll put the question mark here because we didn't prove it yet. But we do have this fact, which I'll put in the top corner. I'll actually write it like this. I think this will look a little clearer. Cardinality of the edge set of G minus 3 times cardinality the vertex set of G. And like I said, it's possible to get a sharper inequality. So we can get a denominator of 29 instead of 64. We need to assume that E is greater than 7n in that case. But since we don't really care about the constant here, we just care about the omega bound. So we're going to prove the weaker constant, the 1/64th. And we're going to use the probabilistic method to prove that. So with the probabilistic method, we have a graph already, so we don't want to just generate a random graph out of nothing. We have to use our original graph, the graph G, somehow. Now, how do we want to use it? Well, we can still do randomness. What we can do is we can take our graph G and we can build a random induced subgraph of G. How do we want to make a random induced subgraph? Well, we can consider the vertex set of our graph G, and each vertex in G, we can put it in our random induced subgraph independently with probability P. So each vertex gets included in the subgraph independently with probability P. And I just want to emphasize here, this is an induced subgraph. So once we know the vertices of the subgraph, we also know all of the edges, because each edge is included in the subgraph if and only if both of the vertices in the edge are included in the subgraph and both of those vertices have an edge in G. So if we have some pair of vertices that don't have an edge in G, then they do not have an edge in the subgraph. And now we're going to use that useful inequality that we proved on the last slide. So for any graph, we can say that the crossing number of the graph is at least the number of edges in the graph minus 3 times the number of vertices in the graph. So this is what we have up here in this corner. And we can apply that specifically to the random graph that we just generated, this random graph H. We can say that the crossing number of that H is at least the number of edges in H minus 3 times the number of vertices in H. And we can calculate some expectations now. So first, let's define a random variable, x. X, this random variable, will be the cardinality of the vertex set of H. And in order to calculate x, it's useful to define some indicator random variables. So for little v in the vertex set of G, we can define this indicator random variable x sub v, and it will be defined as 1 if little v is an element of the vertex set of H, and 0 otherwise. And we can see then, using those indicator random variables, that our random variable x is equal to the sum over little v in the vertex set of G of x sub v. So if we want to calculate the expectation of x, it's going to be expectation of that sum and here we can apply, as usual, the linearity of expectation. So we got our sum over the vertices of the expectation of xv. So now we just need to figure out what's the expectation of xv. So we look at the definition down here, and we recall the definition of expectation. So I'll put it up here. So the expectation of xv, it's going to be 1 times the probability that xv equals 1 plus 0 times the probability that xv is 0. And 1 and 0 are the only possible values that xv can have, so that's why they are the only possible values in this calculation for the expectation. The 0 part is just 0, so we can not worry about that. So we just have the probability that xv equals 1. And we can look at the definition of xv to see that probability. So the probability that it's 1, same as the probability that v is an element of vh. And we can write that probability v is in vh. We see that each vertex is included in vh with probability p. So each of these expectations, expectation of xv is just equal to p. So we have the sum over all the vertices of p. And we said that the graph had order n. So that's going to be p times the order, so just pn. So that's how we got that first expectation of the cardinality of VH. And we also can calculate a second expectation, the expectation of the cardinality of E of H, so the edge set of H. And to calculate that expectation, we want to define another random variable. So we'll define the random variable y, let's say, cardinality of EH. And for each of the edges in the edge set of G, so for each E in that edge set, we will define these indicator random variables. We'll call it YE. It'll be 1 if E is an edge in the edge set of H, and 0 otherwise. And just like we did above, we can write Y, the cardinality of the edge set of H, as a sum over these indicators of the indicators. So for each edge in the edge set of G, we include the indicator Y sub that edge. And then we can calculate our expectation of Y, which is the expectation of the sum. And then we just have to calculate the expectation of each of those indicator random variables, just like we did above with the other expectation. So here we have reduced the expectation of the sum to the sum of the expectations, again using linearity of expectation. And we can calculate the expectation of YE. So expectation of YE, using the definition of YE, is just 1 times the probability that YE equals 1 plus 0 times the probability YE equals 0. So that gives us the probability that YE equals 1 when we simplify it. And the probability that YE equals 1, this is just the same as the probability that E is in the edge set of H. And the probability that E is in the edge set of H, this is the probability that both of the vertices in the edge E were chosen for the vertex set of H. Both of those vertices were included independently, each with probability P. So the probability that they were both included is just P times P, and that's the same as the probability that the edge was included. And that is going to be P squared. So for every single edge that's in the edge set of G, the probability that that edge is included in the edge set of H is just P squared. So we can write this sum as just the sum overall E in the edge set of G of the constant P squared. And the number of elements in that sum is the size of our edge set. We said that there was E edges, so we get P squared times the number of edges, which is P squared E. And so that's how we got this quantity for this bullet, P squared E, for the expectation of the size of the edge set of this random subgraph. Random induced subgraph, in fact. And we already explained the Pn, which is the expectation of the size of the vertex set of our random induced subgraph. And so combining, we can take this inequality right here, and we can take expectation of both sides. So we can say expectation of that is greater than or equal to expectation of this. Expectation of this side is equal to, by linearity of expectation, this thing right here. So that's why we can say expectation of the crossing number of H is greater than or equal to expectation of the number of edges in H minus 3 times the expectation of the number of vertices in H. And that is exactly this quantity right here, p squared E minus 3 times p times n. And we're very close to the end of the problem now. So you want to prove that CR of G is greater than or equal to E cubed over 64n squared. I just want to note here, E again is the number of edges. E is not like 2.718, different E. So here we're talking about a variable E. So in order to finish this problem off, you want to pick some P. So you need to pick what's a good P to give you that bound. So notice that when we defined our random induced subgraph H, we didn't specify P. So that was on purpose. We left the specification of P until the end. So we want to pick a P that's going to give us the bound up there. So if you try to play around with this and figure out what P should be, you might find some P. But then you might wonder, why right here are we not getting the bound up here? And notice that right here, this expectation of CR of H, this is not CR of G. It's a CR of H. It's expectation of CR of H. And you want a CR of G. So how can you express expectation of CR of H in terms of CR of G? And you don't necessarily need an equality. All you need is an inequality. So more specifically, I want you to prove the bound in the first bullet. And let me be a little more specific about the last hint that I was talking about. So the hint, can you find an upper bound on the expectation of CR of H in terms of P and CR of G? So can you use a real similar idea to the idea we used here and the idea we used here? So can you use perhaps some indicator random variables in a specific plane drawing? So you can take some plane drawing, a special plane drawing. You're going to want to pick the right one. And you might want to take some indicator random variables for some certain crossings in that drawing. And then you might want to look at the expected number of crossings for a certain subgraph in that drawing, maybe. And that drawing is just a fixed drawing, so it won't give you the exact value of the crossing number that you're considering, but it might give you a bound on it. So this hint, what is an upper bound on the expectation? That's why we're asking only for an upper bound, not for an exact value of that expectation. So you don't need to get the exact value for this problem. All you need is an upper bound. An upper bound will suffice to get you the CR of G. But the upper bound, it's going to be only an upper bound, assuming you use a similar strategy to what we used here. And it's going to be because you're going to probably fix a certain drawing when you prove this upper bound. So you're not going to consider all possible plane drawings. You're probably going to be considering a certain plane drawing. So hopefully that hint helps, but feel free to ask me if you have any questions. And that brings us to the end of this video. But in the next video, we'll discuss another graph parameter that's related to VLSI circuit design. Thanks for watching.